some, whoops. While I'm doing this, let me just confirm what Raphael said, that I was asked to speak on the rather expansive set of topics of black holes, firewalls, and chaos. And I was strategic and gave a counter-proposal that I would only speak on two of these topics. Thank you. Black holes and chaos. I have a strategic advantage, though, in that I think I have agreed to moderate the discussion this afternoon. And since firewalls are actually a very puzzling but very interesting argument that has propelled a lot of the work in this field, I think it would be appropriate if we had a little bit of a discussion this afternoon about them. I am happy to see that one of the authors of this paradise, Ahmed Almieri, is sitting in the front row. And you should think about maybe saying a few words this afternoon. So I'll continue with this list of
I don't know if you made it clear that Stanford is not just where you work.
I will make that clear. I will make that extremely clear. Following on Raphael's point, as might be obvious from this, virtually everything that I know about black holes and chaos I learned from my collaborator Douglas Stanford, who's sitting in the front row doing our 2-year-plus ongoing collaboration. So I'm glad that he can be here. It's not the place; it is the place where I work, but it's also the name of my collaborator. All right. So what I am going to talk about is black holes and chaos, and this is a subject that has to do with a system that was formed a rather small part of Patrick's talk. The subject of thermal systems. Now, we'll have to define what we mean. I'm not sure we'll actually have something really satisfying. But as a start, these are systems that are described by a thermal density matrix, normalized by the partition function. And if we want to talk about pure states, we can imagine that this density matrix is purified by this two-sided state that Patrick talked about that we might call the thermal field double state. So, again, one of the marvelous things about this ADS-CFT correspondence, or in a more general framework, the gauge-gravity duality, is that these thermal states also have an elegant geometrical dual. Their dual in the bulk is a black hole, which after all is a thermal system. It has an entropy, it has a temperature given by Hawking radiation, and it corresponds quite precisely to a thermal state in the boundary quantum mechanical field theory. And just to illustrate a few pieces of that, let's imagine that this is the boundary field theory. Here I'm straightening out the circle that Patrick drew, or we can imagine this is a very small piece of that circle. And this is this radial direction, the extra holographic direction. And then in a black hole geometry, you have a certain radius, the horizon radius, at which things get interesting. You might join into this other side of the world, or you might fall into the black hole. If we then imagine computing entanglement entropy, let's say in a small region, we would form this Ryu-Takinagi surface, as Patrick discussed, and it would work just about the same as it worked in ordinary ADS space with no thermal excitations. Let's imagine this is one spatial dimension and this is length L. We would find this characteristic, roughly speaking, an area law. Because it's a conformal field theory, it might go like log L. But if we took a longer interval, the surface schematically drops all the way in, hugs the horizon until it comes back out. And we find that the length of this segment, the analog of its area, is proportional to L. So for this surface, we find that the entanglement entropy is proportional to L. L is the volume here, and so this is a volume law of entanglement. So the volume law of entanglement of thermal states corresponds to having a horizon in this bulk geometry. Okay? And in fact, the entropy is proportional to this length over 4 g Newton, which in these large N gauge theories that are often the dual is proportional to n squared L. G Newton is like 1 over n squared.
So,
Yes?
but in the conformal field theory, it should still be log L, right? So
No, only if it's a thermal state in the conformal field theory. It's in the vacuum of the conformal field theory, it's log L. So I'm thinking of a highly excited state in the conformal field theory. And so it's precisely there that you see volume law entanglement. Right. And the picture, the geometrical picture, again, is very beautiful. You're hugging this horizon. And this, of course, corresponds to the fact that the entropy of a black hole, which is given by the area of its horizon divided by 4 g Newton, which motivated this Ryu Takeyanagi proposal, is that this Bekenstein-Hawking entropy is just the area of the horizon. Okay. So that's one point. But thermal systems have more than volume law entanglement. Okay? They thermalize, whatever that means. You know, roughly speaking, what it means is you take a rather special state, they evolve chaotically in such a way toward a more typical state that has volume law entanglement entropy, looks thermal. Okay? Approximates expectation values given in this thermal density matrix. This is a very difficult phenomenon to study using standard techniques in quantum systems or quantum field theory. It's time dependent. The systems that thermalize best are strongly interacting. It's hard. Okay, and it's been a big problem. Okay, and one of the many great things about this gauge gravity duality is that certain aspects of thermalization are laid out for us very clearly, and we'll talk about some, and we'll talk about some more recent ones discussed here, depending on how far we get. The first indication is that suppose you started from a special state. Let's say in the bulk, that special state corresponds to several massive particles lying around, okay, and evolve them in time. Typically what happens is if you have enough of them, an energy greater than of order n squared, many n squared, those massive particles collapse and form a black hole. That's what happens in general relativity if you watch the time evolution of a bunch of matter. It generically collapses and forms a black hole. A black hole is a thermal state, so typical high energy states evolve to something thermal. So this thermalization process is laid out for us as one of the most generic basic phenomena in general relativity. Stuff collapses to make a black hole. And this is one of the many beautiful parts of this duality. Thermalization is just the most obvious thing there is. Yes? So, yes, in the boundary field theory, I've made some little lies in the service of a bigger truth. In higher dimensions especially, a candidate for this boundary theory would be an SUN gauge theory, and it would be that N. In 1 + 1 dimensions, that's not the easiest candidate, but it's that N. It basically tells you the number of degrees of freedom in this boundary theory. You have fields that have that correspond to n squared matrices, so you have of order n squared fields. Okay, so it's not surprising the entropy should be of order n squared.
Can you just call it C?
No, I can't. Yeah, but I should, but I can't. Okay. But you're not allowed to say. I mean, yes. You see, you just, as usual, Daniel, you've got me off my rhythm. All right. All right, so let me draw one of these Penrose diagrams for that kind of collapse. You might have, here's the ADS boundary, this might be the origin, you start with some matter. Oh, what does it look like? There's a shell of not a shell, but a piece of collapsing matter, it forms a singularity. And at some time during the evolution, a horizon forms. Horizons are 45-degree light rays in this diagram. And so an observer late in time, this is time, looking back in to the system says, there's a horizon and it emits Hawking radiation, the state has become thermal. Okay. So this is a good thing. Another thing that we can do, though, is we can ask about timescales. How long does it take for this bunch of matter to collapse and form a black hole? And the most quantitative thing we can do is we can ask, suppose the system has almost formed a black hole, and what is the very latest stage of settling down? So we imagine linearizing this evolution a little bit away from the static case. And that's something that people in general relativity have studied for many years. It corresponds to something called quasi-normal modes. These are the linearization around the solution. And quasi-normal modes are described by a frequency. This frequency has a real part. There's some oscillations, plus I times an imaginary part. And this corresponds to the relaxation to the pure black hole. This is thermalization. The system relaxes down to this state. And so one can compute rather simply using classical geometry what these quasi-normal frequencies are, and omega imaginary, if the field that's relaxing, like if it's the metric or if it's some other scalar field, not too heavy, that's of order the temperature of the system. Sometimes I'll write this as 1 over beta. So it's the characteristic energy scale. And if we ask for the time scale for the system to relax, it's of order the thermal time scale. Okay. So you have this very complicated system, a strongly interacting gauge theory that would be a real difficult thing to study. But you solving classical general relativity questions, you can figure out the time scale to relax. Now this is what you might guess, but you actually can compute coefficients. And so again, this is one of the marvels of this kind of duality.
Sorry, so
yes?
quasi-normal is going this way or this way?
Things fall in. Things fall into the horizon. Now, in the boundary, this would correspond to some thermal correlator of some field operator. This is some field operator in this boundary field theory. In these gauge theories, this could be like the trace of a matrix squared or something. These brackets are thermal expectation values. This would go something like e to the minus omega imaginary t. It might oscillate with the real part. And this corresponds to the relaxation of this thing down to its equilibrium value. Let's assume the equilibrium value of these things is 0. Yes?
Sorry for a naive question, but is the t the outside observer time?
Yes.
That's why something just falling in normally will look like decaying.
That's right. That's right. And further, you might study more complicated things, thermal expectation value of time-ordered 4-point functions, where the ordering of this thing is as written. Pretty quickly, the stuff that you throw in will relax. And as far as these later operators go, the system just looks like a black hole. So this thing looks like WW, doesn't matter what time, VV, plus order e to the minus omega I t. Things settle down. All right, but these quantities, this is great. This is really a marvelous thing. But these kind of quantities probe a rather preliminary kind of thermalization, a rather preliminary kind of chaos. It might roughly analogous to the kind of time in a hot gas for a particle, a molecule to undergo a few collisions. What's not being answered here is a more refined notion of thermalization, the time it is for each degree of freedom to interact with each other one. Okay, if you will, for all the degrees of freedom to become entangled with each other. And this is a question that people have been looking at more recently in the context of black holes. Now, answers to these questions actually grew out of quantum information. In particular, studies of attempts to make good approximations to Haar-random unitary operators, which are kind of the ultimate in quantum chaos. Okay? And the kind of approximations I'm talking about go under the name of approximate unitary 2 designs. Some of the people in this room have made important contributions to that subject. And from quantum information, these ideas were connected to the physics of black holes by Patrick Hayden and John Preskill. And building on that, actually these gauge gravity dualities by Sakino and Lenny Susskind. And this work of Sakino and Susskind in particular, they advance the fast scrambling conjecture, which is closely related to this work that I hope I'll get a chance to say a few words about. But if I back off a little bit from the science, I can say that this work is another one of these poster children for this connection between quantum information, quantum many-body systems, and quantum gravity. Here the flow was in this interesting direction, and maybe it's going to circle back. Maybe this last paper it circled back a bit. But I think it's a real existence proof that real power and advances can come from this interconnection. So I'm sold. And well, I guess if you're here, you're sort of sold also. So the question is, how do we diagnose this kind of chaos? All right. And for this, I'm going to talk about some of the notions that are described in this very nice paper. Okay. And a way of diagnosing this chaos, and I guess here, let me erase this.
So because this kind of chaos now means the weaker or the stronger?
The kind of chaos where having to do with each degree of freedom interacting with each other. Okay. And I'm deliberately not being more specific than that because these things are defined by, as I described them. Now let's see. Oh, this thing actually sits in a... So let's examine, let's say, in the quantum system, in the field theory, the time-evolved operator. And let's say W is a rather simple operator. It might be the trace of a couple matrices in these large N-gauge theories, or in a qubit system, it might be a single Pauli matrix. Let's think carefully about what these three factors mean. This first factor might correspond to time evolution forward. You evolve in time, and then after you've evolved in time, you apply a perturbation, this W. Then you run it backward. It's this last sector. What do you get? Well, if the system was not chaotic, if it was a free system, basically what might happen is this operator might move. The time evolve a free fermion operator, it moves over according to its velocity. But if there's a lot of chaos in this Hamiltonian, you take the simple operator, you time evolve, ping the system. That ping makes an enormous effect, so when you make this time operator go back, you don't get close to what you started with. And in fact, the operator could be very complicated. It could involve the products of many, many Pauli matrices, say. So a diagnostic of chaos is to ask how complicated this operator gets when you go forward, ping, and go back. How much do you fail to cancel out the forward and backward motion by applying a small perturbation? Now, a way of diagnosing how complicated this operator is ask for the commutator, let's say at time 0, of this operator, sometimes called a precursor in the business. Okay? How big is this commutator? Okay? If this is made of lots of Pauli matrices and this is like a one Pauli matrix, it will fail to commute quite a bit.
Is it important that they are different operators?
No, not at all. In fact, one wants to ask this question for quite general sets of V's and W's. Okay. And one can give a numerical diagnostic of the size of this commutator by taking its expectation value in a thermal state. So we could define, for instance, C of T, a number, as equal to the thermal expectation value. Make it positive. Let's say these are Hermitian operators. This makes a positive quantity. Okay. And the expectation value is the expectation is in a chaotic system. As time increases, this number will get bigger. And so at short time, for typical V, this will almost completely commute. So this curve might start small, and then at some time it might come up to its maximum value, and I'll tell you what that maximum value we expect is in a minute. And this turn on will be a diagnostic of this more fine-grained chaos.
Expect that some operators will commute with each other.
That's right. So this is a question for a rather generic operator. You have to ask, sort of pick pick an operator that's not one of these special operators where this clicks.
So it's just sort of like, what's the worst case?
Say worst case, yeah. Now, if you write out this commutator squared, you see that you have several terms, 4 terms to be exact. Some of them look like these time-ordered correlators I discussed originally, or close relatives of them. And after a few thermal timescales, those factorize. And so we imagine that this quantity C of t looks like you have 2 such terms. It looks like WW, VV. And then you get some new terms where you have VW, VW, and so on. And in fact, you get twice the real part of a new kind of correlator. This, again, is a thermal expectation value. For early time, these are about the same. You cancel, you get the small part of the curve. But for later time, this correlator does something else. Notice that this is out of time order, 0t, 0t. These out of time order correlators are a crucial diagnostic because they determine this commutator of chaos in these systems. And we can see, inverting this curve, that this out of time order correlator starts big to make this exactly cancel, and then at this characteristic time tails down to 0. When this is 0, this commutator is its maximum. You can see that this is 2 WW VV. We call the time at which this happens a characteristic time for chaos of this strong kind to set in. We call it T star, the scrambling time.
Can you see something like the Gravitational exponent?
Yes. I'll say just a question about it. In fact, that's related to this first tail off, is exactly that. Yeah. Now, an important piece of progress in studying these is that you can compute them using the bulk, using this picture of gravity. I'm, 20 minutes in? Is that, what do I have, 10 more minutes? Yeah, okay, then I'm not going to be able to explain how you do it, but in these papers, okay, we illustrate how you could actually compute these out-of-time order correlators using things in the bulk gravity. The crucial thing is that these out-of-time order correlators are determined by a high-energy collision. These are thermal expectation values. It's good to purify, to make them expectation values in a pure state in this doubled system of a left and a right CFT, okay? And so the dual picture of that is this Penrose diagram that Patrick drew, this 2-sided eternal black hole. And roughly speaking, the collision is a collision between pulses going this way in this central region near the horizons of this black hole. The strength of this collision is determined, and again, we are in a position where we can use some kinds of gravitational perturbation theory. Newton's constant that determines the strength of all gravitational interactions times the energy of this collision squared. Because I'm at Berkeley, I'll call this Mandelstam S. Okay? That's the center of mass energy squared in a collision. It's not the entropy. The fact that the amplitude for this process grows with energy is a characteristic of gravity. Gravity is a process where interactions grow with energy, unlike gauge theories or vector particles. And this is crucial to the onset of chaos. So what I will do is I'll try to give you at least a heuristic for what little s is. What is the energy of this collision? Well, roughly speaking, I'm not talking about this anymore. We're imagining inserting an operator here at a time, let's say an early time minus t. And we're asking, what is the energy of the pulse this operator emits? Let's say in the reference frame determined by these horizontal and vertical axes. Well, this picture has a symmetry. If you move time up in this direction and time down in that direction, it leaves the picture unchanged. This is the symmetry of the thermal field double state, where you have energy on the left, energy on the right, tensor product. If you apply a positive Hamiltonian to one factor and a negative Hamiltonian for the other, it leaves the state unchanged. That state has a symmetry. That's this symmetry. Well, you can see on this picture that, however, let's go down in this direction, it pulls the pulse down further and further toward this horizon. In the middle of this region, you basically have ordinary Minkowski space. You take a little piece of this geometry, it looks like Minkowski space. Here's a symmetry that if you act with it more and more in Minkowski space, you happen to hit a light cone. What is the symmetry that if you act further and further in Minkowski space, you end up with a ray on a light cone? It's a Lorentz boost. Further, this time is an additive parameter in the symmetry. The additive parameter of Lorentz boosts is called the rapidity. And so this time plays the role of the rapidity of Lorentz boosts. Well, the energy that's created by a boost of rapidity t is exponential in t. So the energy squared, little s, is equal to e to the t. And the right coefficients, beta is the natural time scale, and there's a 2 pi here, basically because things have to be periodic in imaginary time with period beta.
I mean, maybe it's, just to be clear, the invariant thing is that you've got this other operator, and
Yes.
there's a piece that's going back in time.
Yes.
The center of mass collision of those two.
That's right. And so I put that in by asking for the energy in this particular reference frame. That's what picked out that process.
And you put the other operator at t equals 0.
That's right. That's correct. And then I need a scale here. Let's call it the temperature squared. Okay. So then this strength of the collision becomes 1 over n squared, the number of degrees of freedom in this gauge theory, e to the 2 pi t over beta. And the temperatures, let's ignore them for a minute. And so the effect of these operators on each other is proportional to this. And we can ask, when does a term like this get to be of order 1? Okay. Well, this effect is order 1 at a particular time. Let's call it the scrambling time, t star, equals beta over 2 pi log n squared. This is the characteristic time at which this thing breaks away from its early time value. The fact that this depends exponentially Kitaev, who also did this calculation, characterized this exponential. He said we should think of this as a Lyapunov exponent, something increasing with time. And this says that if you use Einstein gravity, the Lyapunov exponent is equal to 2 pi over beta. What we've recently been able to apply, to give very strong arguments for, is that in any thermal quantum system with a large number of degrees of freedom, the precise statements are contained in this paper, that this Lyapunov exponent is less than or equal to its value in gravity. This argument doesn't use gravity. It's just a feature of quantum mechanics. But it says that this chaotic development in a system with many degrees of freedom can happen no more quickly than in the system with a black hole dual. So again, we've been able to use the power of gravity to actually compute chaos. And then motivated by this, we've been able to prove in quotes, but give a strong argument for a bound that says things happen no more quickly. So this is actually, again, backing off to strategic questions, this seems like a very powerful technique in using ideas from gauge gravity dualities to get inspiration from them. And then with those results, go back and try to make more general statements that these may bound or that these may suggest the structure of. I'm basically, what do I have, 5 more minutes? 5, okay. All right.
Do you expect that to be a bound and not just this example?
Yes, we expect it to be a bound.
I said, why do you expect it to be a bound?
You want me to give a summary of this argument?
Because you expect the black hole to be scrambling as quickly as anything else?
There's a CFT argument.
There's an argument that's independent of gravity that establishes this as a bound.
Well, it would take too long.
Do you want me to give a
Yeah, that'll be hard. I mean, that's
Yeah.
a whole paper. So
Maybe offline.
maybe we can include it in the discussion.
yeah, all right. But,
I think that
well, okay, I'll give you one statement, that it's very hard. The crucial thing is these correlators, these out-of-time correlators, or a generalization of them, are analytic in time. Okay? And if things were to decrease very quickly as a function of real time, it means they have to oscillate very quickly as a function of imaginary time. And that, roughly speaking, means that if along, let's say, the real-time axis, a suitably defined correlator decreases, if you go a little bit up in imaginary time, it'll increase. Chaos doesn't like to make things increase, okay? And so putting those pieces together, you develop a bound. Okay, that's all right, the taste. Okay. Well,
Sorry, to be clear, the precise statement is that this function CFT behaves like that for a while, and then eventually it saturates it?
yes, the precise statements are about a variant of, not CFT itself, but a variant that's suitably smeared. But a variant of, let's say, of these out-of-time order correlators stays like this for a long time and then breaks away.
So that one's decreasing, that's why I wanted to...
The one, well,
It grows, that's why I wanted to...
the one that's bounded is one that naturally decreases. Okay.
Okay, but then you have to pass this GS through some filter to turn it into that.
Yes, you can directly compute these things that decrease using GS, using the collision argument. Okay, well, let me then turn to some questions then, as a way to ignite some discussion. So here's some questions. We have a bound that we have a strong argument for, motivated by gravity. I think this is actually the first one, a bound in a thermal boundary theory that we actually have a strong argument for. There should be others. What are the others? In particular, there's a very famous conjecture of something related to this, the so-called viscosity to entropy density bound of Kovton, Steranetz, and Son. And they conjectured that this is greater than or equal 1 over 4 pi. The way viscosity works, it's a very curious quantity. The bigger the viscosity is, the fewer the collisions are. Okay, so this is a statement, again, about the frequency of collisions. And in particular, if you process this, this means that there's a time scale, T collision, if you will, that's greater than or equal to h bar over K Boltzmann times the temperature. This bound, if processed accordingly, says that there's a time scale, the Lyapunov time, that's always greater than or equal to 1 over 2 pi. So we see the emergence of a time scale in these systems. This natural time scale you make out of h bar and kt. And it seems very hard for a system to do something dramatic on time scales shorter than that. This is something that an uncertainty principle argument would yield. Given this new progress here, it may be time to revisit this bound. We know it's violated by small amounts, order 1 over n. But perhaps with a little more work, we can get a result that actually applies. So that's a question. And maybe there are other results like this involving this time scale that we now can establish precisely using technology like this. A second question. In classical chaos, if you know that sort of for anywhere you are, let's say in phase space, that you have Lyapunov behavior, that phase space trajectories separate exponentially, which this is evocative of, then you know the system does better things. It's mixing, which implies ergodicity. It really obeys the strongest criteria for chaos. Does something like this happen in quantum chaos? Does this kind of exponentially growing behavior for general operators, does this imply that the system might, for instance, obey the, so lambda L, does this imply the eigenstate thermalization hypothesis? Or the stronger definitions of scrambling that exist, that let's say any subsystem with less than half the degrees of freedom looks thermal to high accuracy? Is there some way from going to short time chaos to longer time chaos? That's probably very difficult, but it would be interesting to know. And a last question for discussion. I would say that our understanding from the bulk geometry of this T star time scale, that sometime I should probably write it, that T star log of the entropy of the system, capital S, not Mandelstam S. I think we're getting a pretty good understanding of this T star time. The next time scale that we know something about is the entropy time, sometimes called the page time, which is like beta times the entropy of the system. For simple correlation functions, this time scale produces a behavior like this. If we look, let's say, at V of t, V of 0, thermal average, it decays, as I explained, and it keeps decaying all the way out to this entropy time, where it has a value e to the minus some omega I s. And on general grounds, if you have a finite entropy system, things cannot get smaller than that, at least in root mean square. So then the thing starts oscillating around. What features of the bulk are responsible for these oscillations? This has something to do with the finite entropy of the system. It may be related to the fact that this smooth geometry actually has a graininess, telling you that the horizon actually has a finite number of bits in it. What is the picture there? And usually in physics, if you can't have a full understanding, there's some hint. There's some hint happening here. Can you make a first hint about what the correction is to ordinary black hole geometry that start responsible for these wiggles? What is it? And last, go down. Firewalls. What does this all have to do with firewalls in particular at this time? Is this the diagnostic in geometry? All right, that has to wait till this afternoon. Okay, I think there I'll stop and we can continue talking about this. Thank you. Yes.
I have a question about the second question.
Yes.
So I mean, it seems that I can consider systems which has infinite number of conserved quantities, but not like a complete set. But I still have some part of it, which is, I mean, it's like a restricted Gibbs. Right? It's like I can have thermalization in a restricted part.
I guess the question is that possible?
I mean, it seems that nothing forbids me to have a thermalization in a subsector of the theory, in which case I will have the lambda L for some operators, but not for these conserved quantities.
Well, I guess the question is, are there reasonable systems that do that besides tensor product systems? I mean, are there? Do you know of an example with many degrees of freedom that actually does that?
Well, at least I know there are systems with, say, I have 3L qubit.
3L qubit?
Sorry. Say I have 2L qubits and
2L qubit.
L conserved quantities. So it's not completely solvable, but you can use the conserved quantity to reduce it.
But does it have like a reasonable Hamiltonian, a local? What system do you mean?
It's a Gravitational model on Hamiltonian net. Well, a generalization of that. No,
Is that system strongly chaotic though?
I don't know, but there seems no reason. I mean, Gravitational model is solvable, but I mean the generalizations we can have part of the conserved quantities reduce their degree of freedom, but then the remaining degrees of freedom are not solvable. At least it doesn't seem there is a reason there. So I just mean there is no reason to forbid like this kind of thing.
Well, that would be interesting. Maybe that's what one needs to do to make this precise. Our experience in the Hamiltonians we know about is this doesn't happen very often. Although there's an important glitch in these gauge gravity duals. People have found some solutions that seem to behave non-chaotically, even though they have high energy for a long time. But well, okay. That's what this question is kind of about: is how often that happens. Is that highly non-generic? If you apply a small perturbation, is that stable? I mean, does it have KAM kind of stability or not?
Actually, there's a very big mathematical physics result on that, or almost a proof,
Yes.
which was in the context of many-body localization, which
Yes.
is the idea that an explicitly disordered systems breaking translational invariance and so on,
Yes.
you can have a stable, non-ergodic phase.
Good.
Even at finite
But
temperature.
those won't have Lyapunov behavior at all.
That's right. No, I mean, I guess the point is, yes, but that would be avoiding ETH, which we knew was possible in integrable models, but in a very unstable way. It was only
Well, actually, is it unstable in integrable models? I thought there was a KAM kind of stability.
in the thermodynamic limit for
Oh, sorry, in the thermodynamic limit. Yes, that's correct. In the thermodynamic limit.
But there is, so
Yes.
MBL examples by Imbri, for example, are sort of showing that it must be quite subtle which systems do achieve the ETH, even if we only consider stable systems.
Yeah. I was giving myself the strong power of saying that there's a Lyapunov exponent to get us a little bit of the way. I think that easily rules out those examples. So I guess.
You can also rule out anything with. Well, I mean, with extra conserved quantities, there will be things that don't have a Lyapunov.
I think that's right. So maybe I should have answered that as a better question.
Well, I guess to clarify, yeah, I thought you mean some of the operators.
No, I want all the operators to do this.
Then
Yeah. Okay. So I want all the operators to have short time, just like the theorems in classical chaos. If you have a phase space where things strongly expand, that's where it's easy to prove good theorems about chaos. And the question is, does that exist here? That's the question. Yeah, I should have given a sharper answer. Thank you. Yes.
This probably is a dumb question. So
There are no dumb questions here.
I was happy with, you'd be surprised. I was happy about that the two-time correlation of your operator V would reach some kind of equilibrium
Yes.
within thermalization time, which is just the temperature.
Yes. That's your. Yeah.
You talked about the two-time correlations between distinct operators, V and W.
A two like VW, just a 2-point function, or a 4-point function.
Maybe 4.
Okay.
So anyhow, this was where the T star.
Yes. That's a 4-point
I'm
function.
wondering how much does that depend on your choice of V and W? I was imagining that, let's say V is basically, the value of this spin
Yes.
projection, and W
Far away in a local system.
projection, and we're, let's say, going to equilibrate toward a ferromagnetic state, right? So at some point, these guys are going to be relaxed toward being correlated.
Yes.
But the time scale for that is clearly going to depend on the distance between them. So
Good.
where does distance show up in your measurement?
Yes, I was quite. I deliberately elided that. An important extension is to think about things localized at different spatial points. Then there will be a velocity, something like the Lieb-Robinson velocity, that tells you how long you have to wait for this phenomenon to set in.
Yeah, so there I don't really see what the role of, a Lyapunov exponent is. I don't see that is something that would, I don't see that as exponential behavior. I see
Well, if you think about the Lieb-Robinson bound, actually there is an exponential growth in these commutators. And it's balanced against some exponential decay in something else. And that's where the Lieb-Robinson velocity comes in. So actually Lieb-Robinson does have an exponentially growing part of the story. You have so many other paths when you compute these commutators in whatever it's called in perturbation theory, when you expand out the Hamiltonians. You have many paths for the terms in the Hamiltonian to take, and they cause an exponential growth. If you look at the bounds, there's an exponential increasing part of time on the right-hand side of the bound. And that's closely related to this.
Can you say quantitatively what happens as you vary the locations of the operators spatially on the boundary sphere or boundary plane?
Yes, you can, and you can compute that holographically. Let me think.
What does that do to your plot of the chaos setting in, for example?
Well, so chaos won't set in at all until you have let me think, you have an e to the t, e to the minus x with some coefficients, and 1 over n squared. So if x is very large, this will be the 2 pi over beta coefficient, and this will be another coefficient I guess we call mu. And in order to make this thing get big, or small, as the case may be, you have this rising t has to overwhelm this growing thing, this decreasing thing in x. Okay? And so balancing those two, you find that there's a velocity. You have to have a certain multiple of t to overwhelm this x. So if suppose these coefficients were the same, you'd have e to the t minus x, 1 over n squared. When does that get order 1? It's when t is of order x plus enough to overwhelm this 1 over n squared. Okay. And so this corresponds to a velocity. In the holographic limit, in the Einstein gravity limit, you find there's a velocity. I guess we called it the butterfly velocity. That's what, 1 over, d over 2, d minus 1, where this is the space-time. This is right? Yeah. This is the space-time dimension of the boundary field theory. It's interesting that the coefficients don't depend on temperature for this. Okay. So you find actually that you have to wait a certain amount of time before an extra time other than the scrambling time if the points are far away from each other. The thing has to propagate out and then scramble.
It just shifts the clip around.
That's right. It shifts the clip around by an amount proportional to this spatial time delay. And so in fact there's a picture of chaos spreading out ballistically from a localized point.
So then T star, it relates to the entropy, so that's measuring basically the size of this wavefront, which is coming past and scrambling. I mean,
Well, one picture is,
then finally over this amount of time, we go from pre-thermalization to post-thermalization value.
one way of thinking about it here, and it's important, is that at each point you have a lot of degrees of freedom, n squared degrees of freedom. This is tied into this mystery that the tensors, have very large index range, that at every point in a large N gauge theory you have a lot of variables. So you have to sort of cause interactions among those variables as well as between adjacent points. So two things have to happen. You have to kind of cause chaos within the degrees of freedom at every point. That's really what I've been talking about here. And you have to propagate chaos between neighboring points. Both of those things have to happen. Okay. Yes?
I was wondering, as a sort of baby step towards 2, do you know whether you're able to usefully bound any higher order correlators, like in terms of this 4-point function? Because you found a new time scale appearing when you went from the 2-point function to the 4.
Mm-hmm.
But somehow the hope is that you don't see much more after that, right?
That's a good question. Let me think. There certainly are some multi-point functions that we've been able to study, and they don't display new timescales beyond this. Okay. But whether there is something else, I'm not sure of. A rigorous bound, I mean, you're asking a real question about a real bound. I don't actually know. Douglas, have you thought about that?
I mean, the only comment that you might make is that in the bulk, it's sort of clear that adding more of these operators and so on, you don't get some qualitatively new thing happening like you did in going from 2 to 4 operators, where you introduced this high energy scattering problem.
Right.
With more operators, you'll get more complicated kinematics for a scattering problem, but the relevant scales are the same.
But the kind of bound that you're familiar with, these kind of Cauchy-Schwarz inequalities, I don't know whether they can stand. It might well be possible to make some precise statement.
Yeah, but I just wanted to add a question.
Yes.
So is this?
I was going to get on my knees, but I think I'll stay standing up. Yes.
You don't need to write it. I'll just say.
Okay.
You can decide whether it's worth writing. So do all conformal field theories that have a large n limit and a large gap in operator dimensions obey this bound? Or in other words, are there, on the list of properties that conformal field theory needs to have a gravity dual, is this a new element on the list, or is it does it somehow follow from the other things on the list?
That's a good question. Or saturate. Let me say saturate. 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 Well, there's things we know about it. You have to ask finer detail questions about what you mean by a large gap. Okay. If you mean a gap of order string scale, then we know the answer is no. There's a small deviation from the bound that's of order. Well, that's n to the 1. That's string scale, right? So I'm sorry, so n to the 1 quarter. You mean Planck scale? Planck.
Yeah, I want to say that there is some low energy field.
Yeah. And Planck, the gap is Planck. Yeah, I think there we have no reason to believe that it won't be saturated. We have the reasons that you know about, which suggest that it is saturated.
I mean, it's not obviously true. I mean, it could be that these are high energy states in the CFT. They don't obviously have something to do with the
So in the
energy
CFT
operator
language,
spectrum.
this large gap means the gap occurs at some scaling dimension of order n, or
N to some power, yeah. But it's a power which is small compared to n squared, so it doesn't obviously have anything to do with what happens in these very excited states with volume law entanglement.
I mean, this of course, well, you know the argument as well as I do, that it looks like the bulk is described by an effective Einstein gravity, and in Einstein gravity, the bulk calculation is as outlined.
In 1 + 1 dimensions, you can wave your hands about modular invariance and imagine that somehow there's some relationship between these very high energy states in the spectrum at low energies.
Yes, I see what you mean. I don't know an argument better than one. I just know we have explicit examples that would satisfy these things. Some of these
theories, you should be able to make black holes. If you can make black holes, you better obey this.
Yes.
That's kind of the intuition for why it shouldn't be a new constraint.
Yes, I think I would agree with that intuition. I don't know of a proof technique to help with that. And of course, there are explicit examples. What's the best example that doesn't have string states? The ADS. No, the Vasiliev won't. Well, yeah, inside baseball. Yeah. Okay.
Joel? Well, I wanted to understand the last comments because I would have thought 1 + 1 spatial dimension CFTs are basically integrable. I mean,
They are not. They are certainly not integrable. The ones, well, that I love and you probably love are often integrable. Okay, but they are not.
But there exist. I mean, there must be something wrong with the ones that are integral because they're clearly not going to saturate.
That's right. They won't even have a Lyapunov behavior.
So which condition do they violate of conjecture number 5? Is it that they don't have the right gap in their scaling dimensions? Or?
Yes, that's correct. Like, for instance, integrable systems have large chiral algebras that create states at rather modest values of the conformal weight. Okay, that'll populate the gap thoroughly.
But even something trivial, N Ising models or something like that.
That's got lots of stuff at low conformal weight. This gap really says that they're
actually scaling with N, or if some power to N.
That's right. In particular, it means there's nothing. This is a graph of scaling dimension, I guess not versus anything. Okay. And the claim is the only things you can have here till of order n to the 1/4 are the stress tensor.
And then is there a sense that in dimensions greater than 1, that's kind of a generic property of CFTs? Because I don't know enough about higher dimensional CFTs, but this is a large class that satisfies.
No, it's not a generic class. It's actually a very special class. Okay, and so the ones that actually would be described by pure Einstein gravity in the bulk are rather special. For instance, in this famous Atouf coupling parameter, you would have to take that parameter all the way extraordinarily large, you know, to be in a situation with a large gap. You just threw darts at this line of Atouf coupling.
But this is a lot stronger even than just saying large central charge and things like that.
It is much stronger than saying large central charge. It is much stronger than that. And you know, the discussion is, morally speaking, it's saying which things are described by Einstein gravity in the bulk. Yes?
For the third question,
Yes.
when you asked about the first hint of the
Yes.
oscillation
Yes.
behavior at long time,
Yes.
we think, wouldn't we say that because there are subdominant saddle points in quantum gravity, and at long time limit, those contributions might be comparable, so
Yes.
the WKB approximation is breaking down?
Yes.
And that would be the first thing I would compute those corrections.
That argument has been explored, and by, in particular, Rabinovici and Barbone have found serious problems in that argument. There's some way that subleading saddle points in real time is kind of not the right thing to do. But that's kind of the question, like what is the right sort of, you know, first correction that we've been around in physics long enough to know that, you know, it's often a good idea to look for the first correction to some reference point, and we don't know what it is, and it's irritating that we don't. Okay. That particular thing, though, people are not optimistic about, I think.
All right, so let's take a break and reconvene at 11:30.